All right, let's dive into a really cool electrical mystery, something that happens inside the very wires that power, well, everything around us. So picture this. You've got a wire, right? You'd think the electricity would just flow through the whole thing evenly. But nope. With certain types of current, the electrons all bunch up on the outside, on the surface. It's like they're actively avoiding the center of the wire. Why? What's going on in there? The best way to think about it is like a weird traffic jam on an electron highway. You've got a big multi-lane road, but for some reason, every single car is crammed into the shoulder lane. It makes no sense. Well, this strange behavior actually has a name. It's called the skin effect. Okay, so the textbook definition is basically this. The skin effect is the tendency of an alternating electric current, we'll get to that in a sec, to hang out near the surface or the skin of a wire. The further you go towards the center, the weaker that current gets. But here's the thing. To even begin to understand why this happens, you have to know that the whole mystery, literally the entire thing, comes down to the type of current we're using. Because, you see, not all electricity is created equal. So let's break it down. You've got two main players. First, there's direct current, or DC. Think of the power from a battery. It's a nice, steady, one-way flow. The electrons just spread out and use the whole wire. Super simple, no skin effect here. But then you've got alternating current, or AC. This is the stuff that comes out of your wall outlets. It's constantly flipping direction, back and forth, back and forth. And this is where things get weird. This is where the skin effect comes into play. And this is absolutely the most important thing to remember right now. The skin effect is an AC-only phenomenon. DC doesn't do this. It's an exclusive club, and DC is not on the list. This is our biggest clue so far in figuring out what's really happening. Okay, so when you hear about this, your brain probably jumps to a couple of really logical conclusions. They make perfect sense on the surface, but they're wrong. So let's play detective for a minute and go through the usual suspects to see why they don't pan out. All right, suspect number one, is it just a delay? I mean, it seems plausible, right? The signal, the electric field that gets the electrons moving, it hits the outside of the wire first. Maybe it just takes a little too long to get to the center. So by the time the electrons in the middle get the message to go left, the AC is already flipped and the message is now go right. Well, as neat as that sounds, it's a big ol' nope. The electromagnetic field inside copper travels ridiculously fast, like a huge fraction of the speed of light. The entire wire knows the current is changed almost instantly. There's just no way a delay is the cause. So suspect number one is officially busted. Okay, let's move on to suspect number two. What about inertia? You know, the good old, an object in motion stays in motion thing. Maybe the electrons are like tiny little cars that get going in one direction, and they just have too much momentum to slam on the brakes and reverse instantly when the AC field flips. Seems reasonable. Yeah, another good guess, but another miss. The world inside a wire is absolute chaos. Electrons are constantly smashing into the atoms of the copper. We're talking every 10 times femtoseconds. A femtosecond is a quadrillionth of a second. It's so fast. They basically forget which direction they were headed in an instant. So their own individual momentum, it means nothing. It's not the answer. So wait a minute. If the inertia isn't with the electrons, where is it? This is where we get to the real answer. The inertia, the resistance to change, it's not in the particles. It's in the magnetic field that the current creates around itself. That field stores energy and it hates to be changed quickly. This right here is the key to the whole puzzle. And that clue leads us directly to the real culprit. It's not one single thing, but this amazing chain reaction that's happening inside the wire. And it's all because of these little troublemakers called eddy currents. Okay, so let's walk through this step by step. First, you've got your AC current, flipping back and forth, right? That constant change creates a changing magnetic field inside the wire. Now here's where the magic happens. Physics tells us that a changing magnetic field will create or induce little swirling electric currents inside the metal. These are our eddy currents. And here's the final piece. These eddy currents are strongest right in the middle of the wire. And, critically, they flow in a direction that fights against the main current. They create a back pressure, pushing the main flow of electrons away from the center and out to the edges. You know what's so cool is that this is a perfect real-world example of a fundamental physics principle called Lenz's law. It basically says that nature doesn't like change. So when you induce a current, it's always going to flow in a way that fights the very change that made it.
The eddy currents are fighting the main current, and that fight is happening most intensely right at the core of the wire.
I love this way of thinking about it. It's like the AC current is creating its own self-repulsion. It's generating this force in the middle that it doesn't like, so it runs away from it. And where does it run? To the only place left, the outer surface. It literally hugs the skin of the wire to get away from its own effects. So there we have it, mystery solved. But so what? Who cares if electrons flow on the inside or the outside of a wire? Well, it turns out this has massive real-world consequences, affecting everything from the power in your home to super high-frequency technology. To actually deal with this, engineers have a term for it: skin depth. It's basically how deep into the wire the current goes before it drops off significantly, down to about 37% of what's on the surface. And here's the rule of thumb, the most important part. The higher the frequency of that AC signal, the thinner and thinner that skin depth gets. Let's put some numbers to this. For the electricity coming out of your walls, which is at 60 Hertz, the skin depth in copper is about 8.5 millimeters. That's actually pretty deep. It means for most wires in your house, this effect doesn't really matter much. The current is pretty much using the whole wire. But now, check this out. Let's crank up the frequency. At 1 megahertz, that's a pretty standard radio frequency, the skin depth in that same copper wire collapses to just 0.066 millimeters. That is thinner than a human hair. Think about that. The electricity is only flowing in this microscopically thin layer on the very surface. The entire middle of the wire, all that copper, is doing absolutely nothing. It's just dead weight. And that has huge implications. By forcing the current into a smaller area, the skin effect jacks up the wire's resistance, but only for high frequencies. This is a massive headache for engineers. It's why for things like radio antennas or microwave gear, they get creative. Sometimes they'll use hollow pipes instead of solid wires. I mean, why pay for a solid copper core if the electricity isn't even going to use it? Or they might take a cheap material and just plate it with a super thin layer of silver, because that's the only part that matters. So let's bring it all home. The next time you think about electricity flowing through a wire, remember this one key thing. That weird behavior where the electrons avoid the center, it has nothing to do with the electrons themselves. It's all about the field they create. As the source material puts it so perfectly, it's the inertia of the electromagnetic field, not the electrons. It's just this incredible, invisible dance between electricity and magnetism happening all around us all the time.